Welcome to rotational energy and momentum. We like to rotate. We like energy, we like momentum. Let's put them together. Along with greed. Here we go. Just like with kinematics and forces, rotational energy and momentum uses the exact same formulas that we already know. And we already know all the analogs. So wherever a mass was, we're going to put I. Wherever V was, we're going to put omega. Wherever, I guess if we have an A, we put alpha. We don't really, it's mostly V. So we put them all in, and we know the formulas. Now the thing that makes it a little complicated is that we can have both translational and rotational at the same time. We'll give a couple examples of that, and it looks complicated first, but bear with me. Things simplify until they're pretty much the same thing. Here's our first example. Kinetic energy of rotation. We have our kinetic energy formula over here, and we know if we use I for M and omega for V, we get this for our rotational kinetic energy formula. And we can use this formula like any other energy. We can say energy goes from potential into rotational energy. We can set mgh equal to 1/2 I omega squared. We could even say these two equal. We could say an object is moving really, really fast and it hits another object, stopping. The other object starts to spin using all the energy up that was in 1/2 mv squared. We could set 1/2 mv squared equal to 1/2 I omega squared. It's an energy just like any other one. And so all of them can be set equal to each other. We're just giving you another one you can put in. Now, let's do an example that shows you how they get a little more complicated. If we want to know the total energy of a rolling object, something that's round, that is moving around like this, but also moving in that direction, it has both 1/2 mv squared and 1/2 I omega squared. But to make things a little more complicated, these two things are related. So when we have I omega, we know that I of a disk is 1/2 mr squared. We know that omega is V over R. We can plug those in for I and omega. And then it looks pretty complicated. But because we have this R and they cancel each other, we are left with just 1/2 times 1/2 times mv squared. So it's 1/4 mv squared. So essentially when we add it together with our regular kinetic energy, we get 3/4 mv squared. So if we have a ball sliding, it's going to have 1/2 mv squared. If it starts to roll, then its total energy is going to be 3/4 mv squared. This leads into our massless pulley with mass problem. Let's first do it with the no mass over on this one here. If my pulley has no mass, I just have to worry about these two masses that are being pulled. This is going to drop a height h. That energy, potential energy of gravitation, is going to go into the kinetic energy of both of these masses. So mgh is going to go into 1/2 m plus m, because both masses are going to move, times v squared. This 2m will cancel with my half, and I'll get mv, and my m's cancel. I get gh equals v squared for my massless pulley. Nice and easy. If I put in a pulley with mass, I'm going to give it the same mass as the other two masses, so they're all m's. Nothing changes in my first two equations. I'm going to get mgh and then a half and 2m there. But I'm also going to add 1/2 I omega squared. I know what I is for a pulley. It's 1/2 mr squared. And omega is v over r. So I can cancel out my two r's. I'm left with 1/4 mv squared and the same mv squared I had over on this one. And they combine to 1.25, or I could do 5/4, I guess. mv squared, and my m's cancel. So essentially here, gh equals 1.25 v squared. So essentially whatever energy I started with over on this one, it's going to make this one go faster than this one because I have a factor of 1.25 in there that's going to affect its speed. So the fact that there's a pulley there makes the whole system move a little bit slower because some of the energy goes into spinning that pulley. But you can see this is a pretty complicated line here. But as I get farther down, all sorts of things cancel and it ends up being not too complicated. Snack time! Today we're having one of my favorite snacks that I use to confuse people. Look, it's healthy. It's peas. But really it's not. It's just crunchy like a chip, salted like a chip. But you can convince your wife/parents that you're really doing it because it's green and good for you, and peas are, you know, a good source of fiber. and 40% less fat. And oh, compared to regular potato chips, yeah, well, those aren't so great, are they? These, however, taste amazing. You need to get some of these. You need to try them. Got a new HB right over there. Yeah, get them. Yum. Okay, on to angular momentum. Our equivalent formulas here, P equals mv becomes L equals I omega. So for things that we do an I for, like discs or balls or pipes, we're just going to use whatever I they give us, like 1/2 mr squared, times over omega. Sometimes we might put in the v over r stuff for both those two if we want to simplify a bit. But for point masses, we use point masses a lot. Like if you have a planet going around the sun or the moon going around the earth, it's a point mass, just one object moving, not an extended mass twisting. We can put mr squared in for our I, we put v over r in for omega, and then the r's cancel, and we get mrv. So this L equals mrv, which was actually in one of your formula quizzes, that is a formula that stays constant if there's no outside torque. And so if we have a planet going around the sun, we can take something and go in or out. And if we apply our force in or out, the r is going to be 0 because there's no perpendicular force. The force is going towards the thing we're pivoting around, which is the center of the planet. So there's no external torque, and so mrv stays constant. If that's the case, if our r gets smaller, our v has to get bigger. Or if our r gets bigger, our v has to get smaller because mass isn't changing. And so you may do some things where you set mvr equal to mvr. If it's a mass, a planet going around and you jet towards the planet or away, like, probably a satellite rather than a planet. Also, this applies to when you're doing an ellipse. Remember the video? If you have an ellipse and you're going from a large R over here into a small r over here, you know that the v has to be bigger here than it is over there. So that when you do the mass, which doesn't change, times vr, this equals mvr on the other side. So essentially the point masses are pretty easy when you do them separately. The I omega was I omega. If you change your omega is going to get faster. That's the ice skater. If your ice skater is out like this, her I is going to be very large. As she brings her arms in, I gets smaller because it's mr squared. R is getting smaller, and so I get smaller, and so your omega goes much, much faster. That's the whole spinny thing. It gets complicated if you have to do both, so let's try that once. So again, conservation of angular momentum, when our net torque is 0, we can set that momentum before equal momentum afterwards. So I can have a force as long as it's straight towards my fulcrum or away from my fulcrum, or I can have no force. I can just sort of be coasting. But if I give it a force, like if my satellite has a rocket on it that's going to push it faster, then my angular momentum is changing. That's a more complicated problem. We don't really deal with that. But if it's a planet or a satellite, I set mrv equal to mrv if I have no torque. If it's an extended objects, I omega equals I omega. So if I change the I, it'll change the omega. Gets complicated when I do both. Let's say I have a particle of mass m that's going to go in and hit a record player. Let's say the record player has the same mass m, just to make things easier. The blob has a mass v. It hits the record player that's at rest to start with. And so I'm going to say L equals L prime. The starting L is just going to be the mass since this one's 0 at rest. So I just have mrv on this side. On the other side, the blob is still going to move afterwards. And so it's going to have a v, but I'm going to call it v prime to indicate that it's after the collision. And I'm going to have I omega prime for the whole record. But I can plug in for I and omega. So if I put mr squared in for I and v prime over r for omega prime, I can cancel one of my r's and I get 1/2 mrv prime there and mrv prime. So I get 1.5 mrv prime, cancel both mr's, and I get, solving for v prime, I get 2/3 of v. And so I can pretty quickly find out the change in velocity of the blob from hitting this. I can also take this one the other direction to find omega. I'm not going to do all of that, but I'm going to do one little bit for you. I'm going to say I could go m, r, and then for v prime, I can put in r omega prime, and then I can add I omega prime. And if they gave me enough information, I could solve for omega prime instead of solving for v. So on all the cases so far, I've been solving for v's instead of omegas, but notice I can go the other way. I can plug in for my v instead of for my omega, and then I'll have everything in terms of omega, and I'll be able to solve. Essentially, all of these look really complicated. This line looks really complicated, but as I simplify out, it gets more and more simple until I end up with a pretty easy answer for all of this angular energy and momentum. So here is my big old long list of all the linear things, all the rotational things, and it's all pretty straightforward. It's all pretty much the same. These last two are a little more complicated because when you relate them together, you have to simplify and you have to get it complicated then simplify back down. But essentially, this unit is just taking what we know, applying it to rotational, and then dealing with a couple complications, which you will get on Quest tonight. You now know enough to tackle rotational. Griegs, my man. There is no 4-3 for this unit. 4-1, 4-2, and we are finished. That means the formula quiz is coming up soon. Be ready. Oh, and by the way, I am the Mountain King.